Yep. Now I just have to get my brain to catch up because I'm still in making slides mode. Okay, so we're going to start by just talking about feature engineering. And I actually really like doing this talk. This is a fun one. But the idea here is we're going to create features that make machine learning work. All right? This is a super important topic. So what is feature engineering? Okay, so this is applying your domain knowledge of the data to create new features that allow machine learning algorithms to work better or to work at all. Okay? It is possible that you can have features that cause your machine learning to not work at all. And that if you fix them, they will work better or work at all. Okay, so it's really, really important. I put it on there twice and then I said it twice. I should like say it 3 times or something. I don't know. It's actually more important than algorithm selection. Okay? And in fact, it's so important that we just often do it for you automatically because, you know, we don't want you to forget. Okay? The key insight here is that these machine learning algorithms have no deeper understanding of your data. They're not sentient, remember? So if you show a machine learning algorithm a number, what does it know about numbers? It knows that they have a natural order that they can be scaled. That's it. Right? 2 comes after 1, 3 comes after 2, that's it. And you can make them bigger or smaller. That's all it knows. If you show it a categorical, what does it know? It knows that those are some discrete values. It doesn't know what they mean or have any understanding of what those labels mean or if things are spelled wrong. It has no clue. Okay, it just knows that there's 10 things here and those 10 things are different. So the magic, the perceived magic, when you see these things and you go, wow, it's magic, is the ability for machine learning to find these patterns quickly and efficiently. It seems amazing, right? It's like there's everything that would have taken you 3 days of playing around with spreadsheets to figure out in 3 seconds. So that's the magic. But these algorithms only know what you tell or show the algorithm with data. If you don't tell it or show it, it doesn't learn it, period. It's not, again, not magic. So if you were to think about this in a medical context, and I give you patient data that has the mass in kilograms and the height in meters, but it turns out that the body mass index, which is the kilograms divided by the meters squared, is a better feature, it's not going to discover that for you. Okay, you have to create that feature. Okay, now there are some cutting edge stuff that will try to explore this feature space and engineer these things for you. But I'm just talking about, you know, your generic off-the-shelf machine learning algorithm. If that feature is going to work better, it's not going to suggest it. Okay, same for a lending situation. If you think about a model where you have a debt and an income column, but it turns out that the debt to income ratio works better, which it does, by the way, generally, it's, again, not going to learn that. Now, you can give it those 2 variables, debt and income, and it'll do a pretty good job, all right? But it often turns out that if you give it the ratio, it'll do a better job just by having the feature expressed in a different way. If you didn't know that until I just said it, that's probably a bit frustrating, right, to think about. You know, you've got 10,000 features or something, and you suddenly have the realization that perhaps they're not ideal for machine learning, that they have to be modified. Okay. But your intuition about this stuff can be risky. Okay, so remember to always prove it with an evaluation. That's the nice thing. You can just make new features and you can try it, and if it works better, it works better. I mean, that's provable. You don't have to guess. There's no mystery involved. So some of the built-in ones that we do for you, all right? When you give us a date time, if you think about a date time field, there's a whole ton of information that's packed into that, right? There's all kinds of stuff you can extract from that string that we as humans recognize as being full of information and computers do not necessarily. And so we unpack it for you automatically. If we see anything that looks like a date time, we just immediately create the year, the month, the day, the hour, the minute, the second. Okay, that just happens under the hood. And your machine learning algorithms are going to learn much better from that. If there's a pattern that's related to a Monday or a Tuesday, it's going to find it in that and not necessarily in that raw timestamp. All right? A similar thing would be categorical fields for clustering and logistic regression. We talked about this at least very briefly in the clustering. But the idea is that if you have a category, the clustering and logistic regression, those algorithms, they require numeric fields for inputs. They're very numeric if you think about it. Remember, logistic regression is basically doing a linear regression of this logit function, and clustering is doing this Euclidean distance measurement. Those are numbers. So you can't input a categorical value into a thing that's expecting numbers. And so, again, we do this transparently, right? We turn the categories into these vectors of integers for you. Okay, and you would go, but of course you do. And I would say, okay, so go pull a random sampling of other platforms and do a quick analysis of how many of them do it for you, and how many of them tell you, oh, you need to do some one-hot encoding here before you run this. Okay, so it is a little different, and it is important. Okay, text fields, same kind of idea, right? We were talking about this. So we've got this, or Charlie was. We've got a text field, and this unstructured text, again, it contains a lot of potentially interesting patterns. And so one of the things we do out of the box is we turn it into this big vector, right? It's a bag of words. So it becomes this big vector of interesting tokens that it discovered. And this turns out to be pretty effective. Another option, of course, was the topic modeling, where you can extract that thematic meaning and use those as new features, as Charlie was mentioning as well. So those are both ways that one that happens automatically, and the other that you can do on your own additionally if you like. Now there's this other little funny thing. This will be your first example of seeing how to engineer features to make things work better. All right, what if your text is not actually unstructured? Okay, so this stumble upon data set that Charlie was showing you, it has a boilerplate field, and maybe I don't already have it loaded. No, I don't, so let me load it real quick. Well, so real quick may have been an exaggeration. This is very small. Okay, I need this one. Okay. So what was in here, so again, just to very quickly, this is just a parameterization of websites, right? So we have all different ways you can parameterize a website: spelling mistakes, HTML ratios, image ratios. And the one field that's in here that is of particular interest right now is this boilerplate, which basically has this raw content of the site. So the text of the site is hiding in that feature. All right, and that was the feature when Charlie was showing you the model that just had all the splits. Okay, like does it contain the words related to cooking? Those were all being found in that boilerplate field. And it turns out if you look at the actual values here, it's not just raw text, it's a little JSON document, right? So there's actually some structure in there. And in this case, they're key value pairs, and you can actually extract those key value pairs out and turn it into a new column that's a text field that's just the title, and a new column that's just the text field that's the body. Okay, all I did was just extract some of the structure from that text field. Now I have two unstructured features from a structure of unstructured features. Okay, and this will actually improve the quality of this model pretty significantly. Okay, do you want to see that one? Or do you just believe me? All right, I see people nodding. No, I don't believe you. Come on. Okay, so this data set is a little different. I've already prepared it. So it has the boilerplate, and down here it has the two new features. One is the boilerplate body, and the other is the boilerplate title, where I've just extracted those text fields. You notice that it thinks they're categorical because they're small, which is, I still need you to fix this, Charlie. So the sample is, it doesn't notice. Okay, so I'm going to fix that, and we'll do our data set. Okay, now let's think about what we need to do to prove this is going to work. We need to do some kind of evaluation, right? We need to have a holdout set. So once this data set is created, I'm going to go ahead and do a trainee and test split. So here again, we have now, this is just tokens for the body of the text, and this is just tokens for the title. All right? So let's do a trainee and test split. I'll just do a one-click random split. I guess we'll do an execution. Despite the waiting every now and then, I always prefer to do these things live. I hate pre-building things. Okay, so let's take our training set. All right, so now we need to build two models, one with the two new features and one without. Okay, so I'll go ahead and configure the model, and the objective is the label. That's perfect. And for this first one, let's take those two new features out, so we won't use them. We'll just do a model without them first. Okay, we'll let that run. And now we'll go back to the data set while that's building. And we'll build another one with those two features back in. Okay, so we have two models now. All right. And while that's thinking, I'll I'll be parallel, and we'll go to this one, which is already done. And we'll go ahead and, so here's our pattern again, where it's just splitting on the boilerplate over and over, okay? We'll evaluate this one. 20% holdout is selected automatically. All right, no problem there. We'll let that evaluation go. And we'll evaluate this one too. And I haven't run this demo in a while, and sometimes we change things, so hopefully this all works. We'll see. Okay, so now we'll compare these evaluations. What do we get? Aha! 7279 and 7289. Okay, so a little less significant than we used to be. We did change the text analysis, but this is the one with the two features separated. And so it does give us a little bit of a boost. Okay, not as dramatic as it used to be, perhaps. It's also possible that I sampled this, but well. Oh, I did. Oh, okay. That's okay too, actually. Yeah, it's pretty careful about ignoring it. Okay. But you can definitely see that it has changed the performance. Okay, there's definitely a difference here. It's not working the same, even though you think functionally the same information is in this data set. Okay. Maybe that wasn't super convincing. Let me give you another one. I want to talk about when the algorithm just isn't going to work at all. All right? So this will be a hypothetical example. So imagine, for example, that you are building some kind of a GPS device, and this is very contrived, so bear with me, that goes into a car, and you're not going to be able to update it. And it's not a GPS device, okay? It just wants to have a general idea that you tell it, I want to go north, and it says you should take this highway. Or you tell it, I want to go east, and it says you should take that highway. It's very generic, okay? But the idea here is you can't reprogram it. So if there's a new highway, you can't go out to everybody's car and put in a new code. So you want some kind of a model that just from the information about the highway can predict what direction the highway goes. That's what you want to do, okay? So you say, I want to go north, should I take Highway 4? And then it goes, no, you should take Highway 5 instead, okay? And so we have a very simple data. This is contrived so that you can see this effect very clearly. So we have highway numbers, we have a principal direction for each of those highways, and we have another feature is whether or not it's a long highway. Okay, I want to drive across the country, or I just want to go next door, okay? And our goal is going to be to predict this principal direction just from the highway number. So let's try it. And this is real data too, actually. This was fun to do this one. Okay. So I'm just going to take a one-click data set. This is no problem. And we'll go ahead and configure a model. And I'm going to predict the highway direction. And I'll let it use both parameters, whether or not the highway is long and whether or not it's east-west. Okay, and here's our decision tree. If you evaluate this decision tree, it actually works pretty well. It's not too bad. Okay. But since we have a decision tree, let's go ahead and introspect this a little bit. So the first split is on the highway number, okay. And if it's greater than 14, all right. And if it's less than 96, and less than 61, and less than 44, and less than 43, and greater than 26, then it's probably north-south. Unless it's long, in which case you got a few more if it's greater than 32 and less than 37. So how many numbers in whole integers are greater than 32 and less than 37? Not very many. And in terms of highways in this data set, you can see there's only one instance in there. There's, in fact, only one highway. Okay, so what is happening here is that it's doing exactly what I told it to, all right? It's using the information it has, which is an integer, to predict some kind of a class, okay, north, south, or east, west. And it's essentially doing that by splitting until it's isolated all of the samples and finally has the answer it can tell you about. Okay? Now, these are US highway numbers. If you don't know, there is actually a pattern to US highway numbers. Okay, you get the sense that this wouldn't work very well with a new highway, right? Because it's just remembering the training data. It's remembering a map. These are all the integers, and these are the north. So if I asked it what Highway 103 would be, it's going to have no clue because it's not anywhere in this tree. But it turns out there is actually a very simple pattern that predicts this precisely, and we can add it. So let's do that. And this is where I'm going to cheat a little bit. Cheating is always encouraged. Okay, so this will be your first introduction to actually adding a feature. So under this icon here, there's lots of things you can do to transform data sets and turn them into new data sets. And one of the things you can do is you can add new fields. And adding a field is basically doing this feature engineering. There's quite a few built-in functions here. So there's lots of discretization, replacing missing values, normalization you can do. There's some math functions. I can take the log of a feature or the square of a feature, for example. There's some sliding windows where you can take samples of data and turn it into a new feature. There's random, there's some statistics you can throw in there, text analysis. In particular, what we're going to be playing with a bit now is these flatline formulas. Okay, and how many people here know Lisp-style syntax? Don't be shy. We know you exist. You're not admitting anything. Okay, but bear with me on this syntax. It can be a little tricky at first, but it's actually very useful in this situation. Okay, so what we're going to do is we're going to make a new feature called don't drop your laptop. Okay, called isEven. Okay, and I'm going to write a very simple expression here that computes whether or not the highway number is even or odd. That's all we're going to do. I don't know if you can see that. Yeah. So I'm just doing a little modular arithmetic. I can call out the field. I can just say the highway number, which is the name of the field. And I can compute mod 2, and if it's equal to 0, that expression is going to be true. And if it's not equal to 0, i.e. it's 1, that expression will be false. Okay? I can also show you a very quick sample of what this new feature will look like. Okay? So here, we can see here for 75, isEven is false, and for 81 it's false, and for 10 it's true. Okay, so it's doing exactly what I want. I can accept this statement and correct this feature. And I'm now constructing a new data set that has this feature appended to it. Yep. So there it is isEven. Okay, and I could even see the function that was used to create. If you want at any time, you can click and say, oh yeah, that's what I did when I created that feature. And let's just go ahead and train the model again. So we'll configure the model, and we're going to predict, again, the direction. And I'm not going to select it. I'm just going to let it use all the features, so it can choose whichever ones it likes. And this is the decision tree we're going to get, okay, which you could agree looks much different, right? And the split is on isEven. Yeah? Oh, yeah. And you know, if isEven is false, okay, so it's an odd highway, it goes north-south. And if isEven is true, so it's even number, then it goes east-west, which is how the US highways are numbered. Okay, all the north-south ones are odd numbers. Okay, now this is also a simpler model, you agree, and also more generalizable, right? We've actually learned a model that is telling us something significant about the highway numbers more than just the integers they are, right? Okay, why am I telling you this? What does this all mean? Where are we going? And this is really important. If you haven't grasped it yet, we'll dwell on it just a little bit. There is a pattern to this data dependent on the even and oddness of the highway number, right? The machine learning algorithm didn't know that until I told it about the even and oddness of numbers. As soon as I created a feature that every row knew something about even and oddness, it immediately found that pattern and said, hey, by the way, when it's even, it's this, when it's odd, it's that, and it ignored everything else. Okay? The reason why is because it doesn't know anything about even or odd. Right? That highway number is an integer. All it knows is that some integers are bigger than others, and you can scale them. It doesn't know about even or odd. If you think there's a pattern in your data set that is going to depend on an integer value being an even or odd, you have to provide that information. If you think there's some pattern in your data set that is going to be dependent on, you know, an integer value being a prime number, you better put that in there too. It's not going to suddenly discover prime numbers. Okay? A pattern that is very obvious to us because we have this enormous domain of human experience and understanding about integers is not in the algorithm. You have to put it there. Okay. That is the game with feature engineering. Now, this is a very contrived example just so that you can see that very clearly. The features that you normally have to create to solve real-world problems are more subtle than this. Okay, but it's the same principle. Okay. Now this is a bit more practical, so a discretization problem. The idea here is that you start with a data set that has a numeric value. For example, these are the total spending that a customer creates, right? Excuse me. So we have this first customer spent $7,304 or whatever. And if you build a model with this where you're trying to predict what your customers are going to spend, you're going to get answers out like, hey, I predict this new customer is going to spend $3,521 with an expected error of 1,232. And that's probably not what you really want from this model, right? Or it may not be. What you might actually prefer is just knowing a new customer if they're going to be a top third, bottom third, or middle third spender. You just want to know if they're going to be a great customer or a customer that you have to interact with more. Okay? You just want them classified. You don't want these precise measurements. Okay, and this is something you can do with discretization. All right, and this is also, this one's easy enough. Let me show you. This is kind of fun too. So we can actually, my keynote expertise. So we can actually create inline sources. And I can actually just paste that table directly into an inline source. And we can do this discretization very simply, so it's not items though. Another mistake. Numeric. Update. One-click dataset. All right, and if I want to discretize this again, I'll just add fields. And I can call this spend category. I can discretize by percentiles. I tell it what field to discretize. I want to discretize total spend. I tell it how many segments I want. I want terciles, quartiles, whatever. In this case, I want terciles. And then I hit create dataset. And now I have a new feature, which is a spend category, which you see has 2 people in the bottom third, 1 in the middle third, and 2 in the top third. Okay, so very easy to convert a regression into a classification problem using discretization. That's a nice tool as well. Okay. So there are just, I guess I kind of already covered this, but the built-ins. So now I've shown you a little bit. There's a lot of built-in functions. This discretization, replacing missing values, normalization. These are all things you can do with that drop-down. Very easy to do. You just click. You want to, do statistics. You can just click on the drop-down, boom, pick it. But of course, you can also write those expressions. So now we have to spend a little time playing with expressions because those are the best thing ever. Okay, so now we're going to write this one together. So we're going to take this debt to income, and we're going to create the debt to income ratio. Okay? But only if I can click. There we go. One more time. Both numeric. Fantastic. Okay, so again, we're going to add a field. Oh, you can do it. Come on. Okay, we'll call it the DTI. That seems like a good name for a debt to income ratio. All right, and we're going to do this. Okay, so the way this works, the very first thing you're going to do is just type a parenthesis. If you're ever not sure what to type, you type another parenthesis. That's probably the correct thing. Yeah, okay. All right, and then the very next thing you're going to do is type whatever you want to do, not the things you want to do it to. That's wrong. The thing you want to do first. So we want to divide. That's what we want to do. That operator goes first. Okay, now we tell it what we want to divide. Division first. Okay, so the things we want to divide, remember, are the debt to income. So we want to take the debt and divide it by the income. So how do we talk about the debt? Okay, well, you can call out the name of the field. So what do we need? We need another parenthesis, of course. Okay? And then we can just say field. Now, field is an operator that's just going to identify that it's going to be replaced by the values of that field in this expression. So I can just name the field. It's the debt. Okay? And the next thing in this list of things is what I'm going to divide it by. So I'm going to divide it by the field income. Okay? And then you have to remember to close all the parentheses. That's very important as well. All right? If you're ever not sure, okay, again, you can use the very handy Flatline editor. It does some syntax highlighting for you. It allows you to validate this expression. It'll say, yes, that's great. If you happen to make a parenthesis mistake, which I make all the time, it will tell you you made a mistake, and then you can fix it. There actually is the the ability to add operators in here. So if I didn't know what a function was called, you can see it tells me some suggestions. Oh, maybe you meant the square or the square root for that. All right, so it'll help you out. Okay, and you can also, once it's validated, as you saw before, you can do a quick preview, and you can make sure that those values for the debt and the income and this new feature we created, which apparently is just called D now, it looks correct. Okay, and if you like it, you accept, and I'll call that DTI, thank you. And when we hit create dataset, there's our new engineered feature. How do you guys like Flatline so far? Too confusing? All right. Okay, a more formal definition of Flatline. It's a domain-specific language. Okay, so we created this. It's not a language you're going to find anywhere else. It's specifically for feature engineering and programmatic filtering. So you can imagine that you can filter a data set like this value is greater than these numbers, a very simple expression. But you could also do a very complicated expression, like you could say, filter this by the cosine of this value or the square root or something, I don't know, whatever it could be. Okay, you want to do a programmatic filter, you can do this with Flatline as well. So again, domain specific, we invented it. It's optimized for speed, that's why we did it. It transforms data sets into data sets. So when you're thinking about Flatline, you're thinking about transforming a data set into a data set. If you're not turning a data set into a data set, you're not using Flatline. Easy, okay? So you can add new fields, you can filter. These transformations are written in a Lisp style syntax. And so we can compute new fields by saying divide, and we can just say the field debt, field income, okay? And for programmatic filtering, you can filter according to functions that evaluate to true, false. Okay. So Lisp style syntax, operators come first. Correct is +1, 2. Not correct is 1 + 2. That won't work. The important thing here is that the data set fields are first-class citizens in this language. So I can just say field diabetes pedigree, and it knows what I'm talking about. Excellent. It has a limited programming structure. It is not a complete language. Okay, so there's a few things like let and conditionals and ifs and maps and some list operators. You can do all the math you would expect, but you're not going to do complex programming languages in Flatline. It's just for doing these little snippets of transformations. Okay, and there's a bunch of built-in stuff. So we've talked a little bit about labeling data. You can do this programmatically too. So you can imagine here is some unlabeled data. In what way is it unlabeled? Well, we have monthly payments, right? So there's Joe Schmo, made a $123 payment or euro, and then failed to make any for the next 2 months. Okay, and there's somebody made 3 payments that are all zeros. And we want to just talk about customers that have clearly defaulted on their loan, right? What do we mean by default? Well, we can just decide that default is missing 3 payments in a row. That's our business. We say you missed 3 in a row, we're going to send you to collections. All right? And so that's an easy label to add. So sometimes labels are easy. Okay? Sometimes they're just a business decision. And that's an example of something you can do very easily with Flatline. Well, maybe. Okay? Maybe we won't do that one. I don't know. Does it look too complicated? You like that one? Okay, so all we're doing is just summing the absolute value of the fields, month -3, month -2, month -1. I'm only putting the absolute value just in case there's like a refund and there's a negative number, I guess. That way, if those numbers all add up to 0, there must be 3 zeros in a row. There's no way the absolute value of 3 integers can be anything other than 0 if they're all 0, or the other way around. The sum of 3 absolute values of integers can't be 0 unless they're all 0. And then I put an equals in front there, and that equals is going to give me a true false out of this. Do you see it? Okay. We'll do something more fun. Maybe we'll do this one. It depends on how many people are asleep by the time I finish the explanation. Okay, so here we're thinking about deviations from a trend. So we've got some kind of a stock price, right? So here's the date, there's a price, and there's some volume transactions. And we're thinking about a 4-day moving average, okay? So we look at this first day, there's no average to compute yet. There's no previous days. There's no day 0, day -1, day -2. Okay, so we have no data yet. On day 2, we know day -1 is 314, so we just put that number right there. That's easy. On this next day, we move this one over, and we put the 315 that was there 1 day ago, and we put it there. And we just keep sliding this window down until we can compute a 4-day average. So it's a 4-day moving average. Okay, if you've done anything with stock prices, this is probably a familiar idea. And then we just keep doing it. And the idea you could do with this is you can take whatever the current price is, and you subtract the 4-day average, okay? And then you divide it by the standard deviation. What does that do? All right, we expect it to change, right? These prices should change, okay? But we don't expect it to change a lot. What we're looking for is when it changes a lot. So we're always comparing the current price to the last 4 days and dividing it by a function that is basically telling us how much we expect it to change, essentially. That's what the standard deviation is. And so if we do this little calculation, if this is a big value, that means that it's a big change. Yeah? Okay. And so you can do functions like this in Flatline. I can just take the field price, and the 4-day average is a built-in function. I can say the average window of the value that is the price from 4 days ago to 1 day ago. And I can compute the standard deviation of a field, and then I can just plug it in. I should make that bigger. But you can just put all those values in and write a big, ugly expression. Okay, it's not ugly, it's kind of elegant. Okay, but we're just taking the price, the average window, and dividing it all by the standard deviation. Yeah? All right. We won't do that one. You can go crazy. It is my personality type that I often go crazy. And so I've done that. So we've seen the highway is even, which is one, actually, I admit I came up with on the airplane while I was looking at a highway beneath me. I was like, oh, that's cool. And you could do the moon phase. Yeah, that's how you compute the phase of the moon. This is based on an approximation, okay, but this is basically computing the phase of the moon by looking at how many cycles, moon phase cycles, it's been since the Unix epoch, January 1st, 1970. So it's a very simple little modular arithmetic. You take the epoch of whatever the current date is, and these numbers are fixed values, and so you just run that through, and boom, you get a thing that tells you the phase of the moon is a percentage. So I did this because I was playing with a crime data set, and I wanted to see if it was true, if there was more crime when the moon was full. I think that would make the most fantastic demo ever, right? But it didn't work out. There was no additional crime that I could detect when the moon was full, unfortunately. You could do that. It's the Haversine formula. Does anybody know the Haversine formula? Well, yeah. This is a formula for computing the distance between latitude and longitude points on the surface of the Earth, or approximating them. Actually, no, it's for computing them exactly. So that is a flatline expression that will do that. Okay, or that is an approximation of the official. We're going to use that, though. So we're going to return to the home value data set idea, and this is my hometown, Corvallis, and I know the real estate market there, and I also know that this university here is ginormous for the size of our city. There's about 50,000 people that actually live in the city, and there's close to 30,000 students that go to that university, not counted in the 50,000 that live there. Okay, so in the fall, winter, and spring, there's 80,000 people in Corvallis. In the summer, there's like 55. All the students go home. And so what happens is that all the houses around here, as they go for sale, get bought and converted into rentals. Right, so it's like everything for a kilometer out is a rental. They're just all rental properties for the students. And that, of course, creates a dramatic pressure on those homes. And so you have these homes that are like 100 years old, and their foundation is tilting like this, and they still sell for twice what you could pay for a 5-bedroom house if you're just willing to go a kilometer farther away. Okay, so I have this knowledge of the market that homes that are near the university should be worth more, and the ones further away should be worth less. And I want to put that information into my model. Remember that data set, or maybe you didn't notice, but it has latitude and longitude, all right? And when you just build that model, it actually learns a little bit from them. But it doesn't learn very well because, again, the model doesn't know anything about Oregon State University or how far home's away from it. If you think that's a signal you want to add, you need to add it. Okay? So that's what we're going to do. We're going to take latitude and longitude, and the reference latitude, that's the center of the university. Okay? Those coordinates never change. And we're going to, and the reference longitude, those coordinates don't change. And we're going to use the Haversine formula to compute the distance in meters between the home, between these two coordinates, the distance between those two coordinates and those two coordinates. Right? These are the same for every home. That's the center always. Okay, and then we'll just let the model, we can just let the model build with that feature as well. Okay, so we gotta understand this first. Give me a minute. No, we're not going to do that. Okay, I did that once already. I don't need to do it again. Here's the idea. Now we're talking about collaboration. I suffered for you. You shouldn't have to suffer, right? I really enjoyed it, but if it gives me the cred, then I suffered horribly. Believe me. So why don't I just take this Habersign formula that I already wrote and wrap it up in something so that I can just give it to you, and you can use it too. Wouldn't that be great? Then you could do this transformation. You don't have to write that formula, that crazy expression. And so that's something you could do with something called WisML. And you guys aren't talking about WisML today at all, are you? You're just going to, okay, I'm going to do like a 3-slide crash course. Okay, all right. I added it earlier today. Okay. But the idea is that we have another domain-specific language. We have 2. We really like being specific in domains with languages. So this is called WisML. And the idea is that you can do these programmatic workflows. So I'll explain that more. But if you think about this Habersign formula, we can think of it like a function, right? This, as a function, it needs some kind of inputs. It needs the data set you want to transform. And it needs this reference, latitude, and longitude. And it's going to do some stuff, and it's going to output a new data set with the feature. That's the distance between these, right? It's a function. It has inputs and outputs. And so what WisML is going to allow me to do is define the structure of these inputs and outputs to that transformation and turn it into a little execution unit. All right? It becomes a program. You take a function and you define inputs and outputs, you have a program. And then I can put it in something called the gallery, and you can just clone it from there, and you can use it to your heart's content. So nobody else has to ever write this again. So, very quick WisML crash course. Okay, WisML is a domain-specific language for automated machine learning workflows. It's a complete programming language. Unlike Flatline, if you want to do it, you can probably do it. Machine learning operations are first-class citizens. So in Flatline, the data sets are first-class citizens. Now, machine learning operations are first-class citizens. You want to do a batch prediction, you want to build a model, you want to build an anomaly detector, those are all first-class citizens, okay? Server-side execution, so this is going to run in the cloud on the server. You don't have to have it running on your laptop and making API calls. But it also is usable through the API as well. So you can run a script with an API call. Okay, so you can create a complex script, make one API call to run it. And they're shareable. I can give them to you, you can use them too. Just so it's clear how this differs from the API, WisML executes in BigML, whereas if you're running something on a program you wrote in Python or something, you're making API calls, okay, and you have to do something locally. WisML, you can run it and then close your laptop and go for a coffee, and when you come back, it's done. Zero latency, every API call has latency over there. The parallelization is built in. If you're using a program yourself, you have to parallelize it yourself, okay? WisML, you can share very easily in the platform. If you write a really cool program and you want to share it, you have to send it to somebody, right? So these are all advantages of using WisML. Also, these idea of code agnostic workflows. You write in WisML once, you can then run that WisML script from any language. You want to do Java or Python or something, that's fine, etc. Yeah, I don't want to belabor that too much. There's a library of script and execution. Yep, there they were. Did you see them? Okay. I do want to make sure it's clear why WisML and Flatline are different, why we have 2. Concerned with resources and concerned with data sets. That one's Turing complete, that one is not. Okay? This one's optimized for parallelization, that one's optimized for speed. That's it, okay? That's all you need to know about WisML for right now. Okay, so there's multiple ways you can avoid never writing a WisML script, ever. You don't ever have to write one. If you love doing this stuff and you want to write one, cool. But there's many ways you don't have to. One is the gallery. So down here in the footer, there's 3 links, datasets, models, and WisML. So there are datasets that are available in the gallery too, and you can clone them and play with the data that's there, so you don't have to come up with your own. But these are scripts that you can clone. So here, for example, is a feature selection script. Here's one that removes anomalies. So it builds an anomaly detector, filters your data set for you, and returns a data set that's clean. All right, very simple to use. So you don't have to do that workflow on your own. And somewhere in here, there's latitude and longitude from a reference point. Okay, if I just click on that, if I like, I can see what the source code looks like. Okay, I can look through what the source code is. So there's that Haversine formula buried in there. I don't have to look at it. Okay, I can just clone this into my account. Clone away. And now I have the script available. Okay, what I did forget to do was actually upload the source. So let me do that very quickly. That'll probably help. And make a data set. Yes. All right. And now what we can do is if I pass it this housing data set, there's some input parameters. So the first one is the data set you want to transform. These are parameters that are defined as part of the script. So if you cloned a different script, it would have different parameters. All right? That's part of the script. And I have the names of the fields. So in my data set, the field is called latitude and longitude. Those are the names. And then I have to give it the reference coordinates, which I've already forgotten. So, because I don't have that memorized. Oh, I went too far. That reminds me of a terrible joke. Here we are. That would help. Okay, reference. Latitude, reference, longitude, and then we execute. And that's it. Hopefully. I haven't run this one in a while either. No, fantastic. Okay, so it outputs a transformed data set. It creates a link there. We click on it. There's our transformed data set. And down here is the distance in meters from that reference point. Okay, so if I have a new data set and a new city and I want to do a similar trick, I can reuse that same script, right? I just put in whatever the data set is, for Seville or something. I pick my reference point. I put in the coordinates, and boom, I do the same calculation. Okay, I don't have to change that WisML script ever again. So that's one way in which you don't need to write your own scripts. If somebody's already created one of these workflows, you can just clone it. Another way is, if you're playing around in the UI like this, and you've done something that's super great, and you would like to make that a script, you can actually do that with this Scriptify. Okay? So because these resources are immutable, and we store everything about how they were created, the platform knows how this data set was created, and it knows it was created from a data set, and it knows that that data set was created from a source. If we'd built a model, it would know how everything before it had happened. If we turn that into a batch prediction and create another model and do a cluster and another batch output, you can have a whole giant string of things that you've done to your data set. And it knows the history of each resource before. And so when you run this Scriptify, it just unpacks that history. So it looks at the resource that you asked to Scriptify and says, how did you make this one? And it writes a little script, and it says, how'd you make that one? And it just builds up. And this source code is now a script that would do that same transformation again. Now, that's a bit weird because I used a script to make it, and then I just scriptified it. But as I said, you can do this for any workflow. Okay, so any resource that you have in here that you've created manually, you can transform into a script. And now, again, let's imagine that I'd done that transformation by hand, and I wanted to do a different city. I can scriptify the transformation, and then I can just upload a new city, put in the reference point, and off we go. Okay. All right. You can go way off the deep end. Can you write a JSON parser? Not really. It's not a full programming language. There's no loops. There's no accumulated values. Okay, so don't do that. I did it, though, so don't do that, though. Yeah, let's skip a few of these. Okay, I do want to talk about this, because now that I've empowered you to create new features, it's important to at least think about this once. Okay? You need to be a little bit careful when you're creating features. There's lots of ways you can be careful. One is you have that model summary. I think we've seen it at least once or twice. If you don't know, every time you build a model, we try to give you a summary of the features that were important in creating that model. So if we were to pull up an ensemble, I don't have one built right now, sorry. If we were to pull up a model, wow, that wouldn't be very interesting. Yep, this one will do. We can ask it for the model summary report, and it'll tell us what features were important for this model. Okay, so this is actually one that's built in the way that Charlie was mentioning. You can take that StumbleUpon data set and do the topic modeling and then use the topics to build the model. So you can see that the cooking topic was very dominant, as was the baking and the alchemy category and a few other things, right? But this is a nice way to introspect the model and understand what features it relied on for building the model. Okay, so when you do your feature engineering, you can build your model, and then you look at the model summary, you can make sure that this looks reasonable. Things that wouldn't look reasonable, or might potentially look unreasonable, is if you have one feature that's like 99%, okay? It just use that one feature, that probably means it's very correlated, like it's actually the same thing, all right? The example I always do is you have a data set with, you have somebody's height in feet and their height in meters buried in a bunch of other things, and you build a model that predicts somebody's height in feet, and it just goes, well, you know, if I know your height in meters, then it ignores everything else, and you just have one feature, okay? That's an obvious example, but you can have features that are very correlated like that that aren't obvious. And you can see that here because you'll see the reliance on that feature. Okay, so the field importance, you can do this algorithmically. There's lots of algorithms you can use, this Baruda, a few others, that will do this feature selection thing for you. So you can say, here's 10,000 features. I just want the 10 most important. There's algorithms that will do this for you. And those exist in the gallery as well. You can clone those and use them. There's this idea of leakage. So I already mentioned this idea of tight correlations, where you basically get models that look like they're doing fantastic, but they're really doing nothing because you just gave it the input that is the same as the output. There's also test data leakage. Okay, we saw a bit of that when I did the diabetes evaluation and I evaluated it on the test, on the training data. Okay, so you can leak information into your test set and get a misconception about the value of your model. But you can also have, and this is the one that is super subtle, you can have this kind of idea of perfect future knowledge. And I always do this at the one slide because this can be very subtle. So imagine that you're modeling a sales pipeline. Okay, so you've got a bunch of steps in a sales pipeline. Somebody puts something in their cart, they put something else in their cart, they click, I want to buy it, and then they have to put in their credit card, and then they have to get a summary, and they have to review it, and they have to click finally OK. And the part where, and maybe there's one more screen where they have to, you know, submit, I'm happy, okay? And you're looking at this pipeline and modeling it, and you have all those steps, and you try to build a model of behavior that's going to lead to the last step. But this n-1 step, right before they clicked on the thing that I was happy with this purchase, was the one where they said, go ahead and finish it. You're just going to get a model that says, hey, if they finish the purchase, they're going to finish the whole process, right? Because the last step doesn't do anything. There's nowhere else to go. You model n, and you're basically modeling the step before. The model has perfect knowledge about one feature before, okay? The same idea for if you try to predict the stock open in the morning and you know the stock close. They're probably really close, okay? Ignoring after hours trading. If you know the price right now, the price tomorrow morning is probably going to be close. And so if you build a model where you tell it what the close price is the day before and ask it to predict the next day, it's going to ignore pretty much everything except the price right before, right? It knows, you know, the last iteration of the stock, it was this. It's going to be really close to that. More crazy things is to remember in this modeling that correlation is not causation. Okay, they're not the same. The example I remember seeing on this was talking about churn and having agents in your department that manage churn, okay? And they were modeling this and looking at the performance of their representatives at re-engaging clients to not churn, right? So they'd leave and then you call them up and you say, please don't leave. You know, we'll make the service better. And you try to get them, and it turns out there were a few of the representatives that were the absolute worst, okay? They had the most terrible performance at retaining these customers. And actually they were the best, which sounds completely counterintuitive and impossible, but what was happening is that because they were the best, the managers were giving them all the most difficult cases. Okay, so although the model was showing you this pattern, all right, it wasn't actually telling you what you thought it was. The fact that it correlated didn't mean it was causing that, okay? They're not the same thing. And this is another one example, real world example, very subtle. Imagine you have a data set with like 1,000 features about a cancer, and you're trying to predict whether or not a patient based on these 1,000 features has cancer or not. You know, the size of the tumor and where it is, their blood tests or something. And somewhere buried in those features is whether or not the doctor ordered a test related to that cancer. Okay? What you've just done is you've told the model that when a trained professional suspects you have cancer enough to order a test, okay, that it's going to learn that's a signal that you probably have cancer. That's probably not what you intended in your model, okay, unless you intended to also include the doctor's evaluation. So that would be a feature that would be easy to miss, okay, that's very correlated to the outcome. The doctor isn't going to order the test unless he thinks you have cancer too, right? So that is another way that you can leak. And last one, this idea that you can have an account ID that predicts fraud. And so I mentioned earlier that we automatically detect features that may not be useful, right? There's a little heuristic, leaves them out. And so the classic example of this is your ID, your personal identification, and so not useful. And somebody came up to me after the presentation. They said that's not always true. We actually built a model where knowing the account ID very strongly predicted fraud. And I was very confused for a moment. And then he explained that, of course, they were running a site that's a bit like eBay. It wasn't eBay, but a bit like that. And what was happening was that they'd already been fighting fraud. And so all the fraudsters accounts had been closed. And fraudsters were only in the new accounts. Okay? And so all that model was telling them was that if they wanted to fight fraud, they just had to stop accepting new people. Right? No more fraud. All right? They'd already policed all the accounts. If they just closed it and said no more people, fraud would be very low. So it wasn't a very useful model, even though the model predicted very strongly that the fraudsters would have these higher account IDs. All right? So, if you don't introspect that model, it'd be easy to be confused that it was performing well when really it's just telling you something you're not going to be able to use. Okay, probably killed that. So we're going to jump around. And we're going to try this too. And I promise I have 3 decks for you, and the last one is going to be kind of fun. I tried to put the fun one at the end. Yeah. Okay. I have a half hour, right? Is it a half hour? Sorry? Okay. I can make this happen in a half hour pretty easy. Okay, so we're going to talk about principal component analysis. It kind of dovetails into what we were just talking about because it is a bit like a feature transformation. And so first, very hand-wavy. And this is the deck that was corrupted, so I'll apologize ahead of time if it's horrible. There are some issues with high dimensionality. So this is just a fancy way of saying that you have a really wide data set. Okay, 10,000, 100,000 features. There can be some problems here. So it implicitly increases your model complexity and may cause your models to overfit. In general, you need to have more observations to generalize well. So you need to have a bigger, if it's wide, you need to have, generally you want it to be longer than it is wide, essentially. You don't want to have 10,000 features and 10 rows. Okay, that's generally not enough. Okay, you want more rows than columns generally. If you have that many features, it's almost guaranteed that some of them are correlated. They're really telling you the same thing. And so you're just putting a lot of noise in there. So sometimes you want to get rid of those correlated variables and reduce it to something that is more relevant, all right? And also the data is really difficult to visualize, right? I mean, we've got the scatter plot, you can play around, but if you have 1,000 features, it's pretty tedious to visualize 1,000 features. Hopefully you agree. Maybe there's like a savant somewhere that can do it, okay? Most people know. It also takes longer to train models or make predictions. Okay, the wider the data set is, it takes longer to train. So that's going to penalize you in the training time. And predictions are slower too, so that's also no good. And so these are all things that you can address with principal component. Now to be fair, you can do it in other ways too. Okay, so for a model, we do this automatically, basically using pruning and a node threshold. So we just don't let the tree grow too big. Okay, and we prune it off. We do that for you automatically. For an ensemble, you can use some of these methods like the bagging or the random forests. That helps with these kinds of issues automatically. Okay, you don't have to do PCA. There's ways to deal with high dimensionality just automatically, all right? For a logistic regression, you can use these regularizations, right, the L1 and L2 penalties, which tries to reduce the importance of these not less important features, if you will. Okay, that happens and for DeepNet, there's this thing called dropout, where you can basically drop out features. Okay? There's lots of ways you can address this with algorithms that already exist, but there are situations where you prefer to do it manually, okay? And so ways you can do this manually is in feature selection, you can preserve the original variables, but just take a subset. So lots of ways you can do this. One in particular is you can just take your 1,000 features and you can build a model, right? And then you can look at that model summary, and the model summary says, I only use these 10. You can go, okay, well, forget the rest. From now on, I'll just use those 10. Okay, that's not very, satisfying, because if you put a new training set in, the importance of the features may change, remember? And so you're kind of putting yourself at a disadvantage for retraining, but it's a practical concept. You can also do this algorithmically. There's all these functions you can use that do feature selection. So and they're in the gallery as well. You can give it a data set and say, here's my 1,000 features. Just tell me the 10 most important. And it'll go through and chug through and tell you the 10 most important. And it'll say, here you go. And then you just use those 10, no problem. There's also this concept of feature extraction. And again, just to be clear, the feature selection, you're just taking a subset. So you have the same features again. Okay, you started with 1,000, you went down to 10, but those 10 are still the same 10 features. They didn't change. You just have less of them. In a feature extraction, you're doing a transformation. You're turning the features you have into new features. Okay, so word vectors are an example, right? You're taking a text blob and turning it into a big word vector. That's a very useful thing to do, so we do it for you. And PCA is in this category as well. Okay, it's transforming the features into new features. Okay, when are you going to use it? So you want to reduce the number of variables in your model, but it's not clear which should be eliminated. That's one situation you might want to use PCA. So you can't just take a subset because you're just not sure. You just want some more generic way to maybe attempt to do a dimensionality reduction. I want to turn 1,000 into 10. You want to generate variables that are not correlated. You know you have correlations in there, and you want your variables to be independent. Why would you want to do that? Well, this is generally because you just really want to, right? Maybe you're going to do a logistic regression. Logistic regression works better with uncorrelated variables, and so you might want to decorrelate them, okay? You're okay with sacrificing some amount of interpretability. Okay, this transformation, the features that come out are not going to be particularly understandable. They are understandable, but not in the way the original features were. All right, they're going to be these weird linear combinations of your original features that don't necessarily apply in the real world. Okay, so in particular, what a principal component is, and I'm sorry for this slide, it's just a linear combination of the original variables. So we just define, here's a principal component. Here are all the original features, feature 1, feature 2, feature 3, all the way up to some feature n. That's our 1,000 features, okay? And each feature, we just put a weight on it. So this is 2 and 4 and -6. And so we have 1,000 weights, and we just add that up, and that becomes our new principal component. It's just some linear combination of everything. Okay, now some of these could be zeros, right? So we could not use some features. Some of them could be negative or positive weights. But we just say, functionally, the principal components are linear transformations of the original features. Now, of course, we have to be clever about how we choose those weights, right? To do anything useful, we need to choose these little W things in some cool way. Yeah? And so that's where this nice little visualization comes in. So the idea, if you explain this visualization right, which I'll attempt to do, it's really useful. Okay, so here we have a data set that has 2 dimensions. It's not 10,000 because I couldn't put 10,000 on the slide, unfortunately. So we're just talking about 2. And maybe we want to try to go down to 1. We just want to turn this into 1 dimension. We don't like 2 for some reason, okay? So these blue dots, these orange dots, and these green dots are 3 classes of our original data set in these 2 dimensions. And what this red line represents is one way that we could project all those points into a new 1 dimension, okay? So we would take all these data points, and the lines are sort of like the projection. We would put them down here. So this data point would go, and we would think about projecting it onto that line. Okay, a little hand wavy. And if you think about this distance here, the idea for the first principal component is going to be to try to place this line so that all these distances are as small as we can make them. Okay? As small as you can make them. And so you can kind of let this thing rotate around. You can see how they're changing shape or changing lengths. All right? Those are all different possibilities for where we could put that new axis, okay? And the one we want is the one that minimizes those distances. And the reason is because if you minimize these distances, you're maximizing the variance. And I know we haven't clearly defined variance, but if you know what variance is, you'll go, oh yeah, that's totally what you're doing. But the idea is that if you let it be that line, hopefully when you were watching that go around, you thought it was that line. Yeah? If you let it be this line, the projection is sort of spread out the most, right? You've got points that are way down here and points that are way down here. And so that line becomes our new one principal component. So what's the second principal component? It's just the one orthogonal in this case, right? We started with two orthogonal vectors and or axes, and we just take it there. If this was 3, we would do a similar analysis in the last 2 dimensions, and the last one would be whatever's orthogonal to that plane. If it was 100, you just do the same thing, you keep reducing it down until there's one left. Okay, no problem. Now, I saw another great video which I've been thinking about stealing, which is that humans already know how to do principal component analysis intuitively. And the idea is like, say you want to take a picture of this bottle, okay? And you want to be able, when you show somebody this picture, you want them to be able to understand what its shape is as clearly as possible, all right? So if I take the picture this way, you have no concept of how long this bottle is, right? And if I take the picture this way, you have no concept about how, well, you have some concept, but it's a little hard to tell that it's round even. It could just be a square or some cube shape or something. And so when you were going to take a picture, you might try doing it vertically, and you might then do it on an angle like this, where I can see both the height and the width of it all in one shot. Okay, and you can think about this as kind of like rotating the bottle around until you have this plane where you can see the most information about the bottle in one angle. And that's your first principal component. Okay, it gives you the most information in one view. Okay. What do you get out, right? You start with some original matrix of variables and you get some transformed matrix. So you get the same number. So if you started with n things here, you get n things out. Okay, so we haven't actually reduced any dimensionality, right? So the game here, though, is that what's going to happen is that these first couple of principal components have the most variance captured, and these last ones generally are just, for some data sets, aren't adding much. And so the game we're going to play is we can just throw some of these out, and it'll still work nicely. That's the game. So the PCA by itself doesn't do any throwing out of dimensions. You do that yourself. But what it's doing is sort of optimizing how good these features can be. It can also be great for visualization. It's a nice way to take a big data set and smoosh it down in a way that gives you a nice visualization because you have these principal components. And I'll show you an example of that. So, excuse me again. A little clarity on how you do this. The workflows have to be a little careful. So we're going to source a data set. We'll do a training and test split. And then we're going to create this PCA. It's an unsupervised method on the training set. And then we're going to do something called a batch projection. And we'll use this same model to batch project the test set. Okay? And when we do this training, we also have to be careful because we're going to be playing with a data set that has a label. I don't want the label in the projection. Okay? Because otherwise I'm going to get principal components that are correlated to my objective. So I have to remove that. Okay? And then we can look at having these new output data sets. Okay, so let me show you what PCA looks like. Okay. So we're looking at a data set of tumors. Okay, and so we have all these features that are in here. So we have a diagnosis field, the categorical at the top, which is M for malignant, and I forget what the other one is. I think it's N for non-malignant. Okay, so we know whether or not these tumors are cancerous or not, or benign, but it's probably benign. And we have different measurements about each one of these, which I think is taken from some X-ray measurements, right? So the radius mean and the texture mean and, concavity. And there's 30 features or something in here. Okay, so I'm not going to do anything. I'll just do a one-click data set on this. And I want to just, actually, let me go ahead and do the training test split before I forget, because I'll forget. So let me just do that now, and we'll immediately start playing with just the training set. Okay, because I'll forget. Okay. All right. Okay, so that we can look at this in the scatter plot. Okay, we can start trying to explore some of these variables a little bit. Maybe we'll do the coloration by the diagnosis. Okay, so each dot is now colored by whether it's benign or malignant. Okay, and we can start looking at some of these variables. So if we look at like the radius mean, and maybe, where's the other one I like? The area mean, there we go. Okay, these are two features in the original data set. One is called the radius mean, and the other one is called the area mean. And you can see these are extremely correlated, right? I mean, we actually give you some correlation statistics here. That Petersen metric, if they were perfectly correlated, would be a 1. It's pretty darn close. Okay, these two features are different values, but they're telling you essentially the same thing in your data. Okay, they're correlated. And in fact, actually, if you think about it, this is the radius, probably of some circle or sphere, and here we have the area. Okay, and you really expect the radius of something that's circular or spherical shape to be related to the area. That makes sense. Okay, that's in fact a well-known mathematical function for transforming one to the other. Okay, so that's the kind of game we're going to play. Is seeing if we can eliminate some of these correlated features and reduce it to something with fewer correlated features. I can't think of a better way to say that. Okay, so this is unsupervised. So we could do a one-click, but I'd need to remove the label. So I'm going to configure the PCA, and I'm going to take the label out. Okay, so we don't have it in there. Because again, I don't want my principal components to be correlated to the label. Okay. Okay, so now a little bit about what you're looking at. These are the principal components. So this is the first principal component that are discovered. And over here we have something called a scree plot. And this is basically showing you the amount of variance that's captured. Okay, the least amount of variance you can capture is 0, and the most you can capture is 100%. So you can imagine that if you capture 100%, that's good news. And if you capture 0%, that's bad news. If you don't know what capturing variance means, that's okay. You just need to know that 0 is bad and 100 is good. All right, and so the thing you can take away from this is just with one principal component, so of the 30 some odd variables we had, this linear combination of those linear variables is already 43.5% of all the variance that could be captured, which is quite high. Okay, and if you want to understand what that principal component is, you can actually highlight these. This is showing you the weights. So that concavity value has a -0.9, and this one has a -0.9, and that one's also -0.9, and they're somehow all related to concavity. I don't actually know anything about tumors, but I can imagine what concavity is. But other than that, I have no idea. Okay, and we can look at principal component 2. There's a bunch of things about fractal dimensions. Okay, but again, it's just these linear combinations that are now structured so that are no longer correlated. Okay, we can also ask for a specific variance. So if I wanted to, for example, just have 90% of the variance, I could do that. And I can see that that's with only 7 principal components, I have 90% of the variance. Okay, and you can see that it goes up very slowly after that. We're just getting a little bit more each time. All right, but if I wanted to do a dimensionality reduction, and I would want to do it in this sort of very formal way, I could say I want just 7. Okay, and I can now create a new data set. This is all kind of wonked. There's our UI guy right there. What happened, Oscar? That really wonked. Okay. So I could say I want 7 components, but I can't click it. It's all wonked. It's really cool when you can do it, though. I'll reload. When in doubt, reboot the website. Actually, I'm the infrastructure guy, so we actually could reboot the website. That would be sort of entertaining. That was a joke. Thank you. Okay, so max components, we'll just say 7. So if we want to do this dimensionality reduction, we can just say, let's cut it down to 7 variables. So that's 8. Let me just type it. The sliders are difficult. And if I now create the data set, it's going to do this computation formally. And that's probably, yeah. Yeah. Okay, so now we have the original features, but we've engineered these 7 new principal components. And actually, if you evaluate this model, just building it with those 7 principal components, which only capture 90% of the variance, I think the AUC is like a 0.97 or something. And if you let it use all original 30, it's a 0.99. So this doesn't do as well, but it's only 7 features. Okay, and it does very, very close with only 7 instead of 31 or 30. Okay, so this is an example of, if you reduce the dimensionality, and we could play this game, I could say, well, what if I allow 1 or 2 more principal components? Maybe it would do better. Okay, but yeah. So there's some magic that's happening here. If you already knew about PCA, we do lots of magic. Okay, normally PCA is just numeric, so we have to do all this extra stuff because if it's categorical or text, it doesn't matter, it still works. There you go. One more. Can you believe it? All right, this one should be fun, hopefully. I think it's fun. I could be skewed. Okay, OptiML infusions, here we go. So remember this? Hopefully this is the same group that was here yesterday, right? There's a few of you now. The people that are still here, you guys are awesome, by the way. You're the cool kids. Okay, so we had this idea of how to choose models for early stage, mid stage, late stage, and the thing that this is too hard. Okay, I don't really care. We don't want to do this. Maybe you do. I mean, so I don't want to be too pedantic here, but if you don't want to do this, there are some other ways you can approach this. Okay, and the other thing I want you to remember is when we were talking about the deep nets, right? We were talking about how we build our neural networks where there's all this complexity, and this is too hard as well. And so we had these two solutions, and one in particular was this network search where you try a bunch of things, and it's a guided search. And so every time you're doing you build one more, you know where to go next to get something better, right? This Bayesian parameter optimization. And the thing you take away from that is that you can do this any parameter selection problem in a similar way. Each resource, trees, ensembles, logistic regressions, neural networks, they all have parameters that impact quality. Okay? And rather than try and error, we can use machine learning to find ideal parameters. Why not just make the choice of the algorithm parameter too? Just do that too. Let it try ensembles and trees and deep nets and with different parameters and do the same guided search. We'll just parameterize everything. Parameterize it all. Okay? So now we have to present a challenge to make this fun. So we're going to start with that stumble upon data set. We're going to do a training and test split so we can do some evaluations. And then we're going to build and evaluate a one-click model, logistic regression, ensemble, and a deep net. We just launch those and evaluate them. And I was going to write a script, but I ran out of time. And then I'm going to show you OptiML. And we'll take the top model that OptiML finds. And then we're going to compare the results using the phi coefficient. Just so we're clear on how we're going to compare, we could use the F-score or the recall or precision or something. We're going to use the phi coefficient. Okay, we're going to explore other ideas for improving performance even further. Okay, so here we go. Did I already split it? That would be cool. No. Do I even have it loaded? No. Okay. Here, stumble upon. Oh, that's the extended, though. I don't want that. Let's use the non-extended for this. Okay. Okay. Let's say we were going to do, yep. You guys all trying this at the same time? Okay. And that's a text, perfect. One-click data set. Okay. So I'm going to configure my training and test split here. And I'm going to use a seed, which is just BigML lowercase. So hopefully this will work exactly the same way it worked when I practiced. We'll see. That's why you can use a seed. That way you get the same split every time. So I don't have to worry about suffering from bad luck. Okay, so here is our training set. Okay, so we can actually do the one-click from here. We'll take the training set, and we'll just go ahead and do a one-click model. And we'll go ahead and do a one-click ensemble, and a one-click logistic regression, and a one-click deep net. And while we're at it, let's just go ahead and kick off a one-click OptiML as well. Okay, so those are all running in parallel now, all those modeling tasks. And we can go ahead and start evaluating some of them so we can see they're running here. So if we take our one-click model, we can go, while the OptiML is running, I'll go ahead and evaluate. That's no problem. So we'll get this one in the bag. Here we go, evaluate. Let's find our ensemble. Here it is. Let's go and evaluate that one too. Did I say a one-click ensemble? I have to remember what I'm doing. Yep, okay. Good news, I'm doing it right. Okay, we'll do the logistic regression here. Okay, here's our logistic regression for stumble upon. That looks nice. We'll evaluate it. Okay, let's see how our deep net is doing. Okay, how are you doing? You know, the next time I do this demo, I'm going to write a script. It'll be a nice dovetail into WisML, right? I just say, and we'll just run this WisML script. Okay, that one's actually still running. So let me show you the OptiML while this is going. Okay, so what OptiML is doing, and I actually, to be really rigorous, since I did a one-click, let me show you what you actually can do with OptiML. Okay, so if you configure it manually, you can specify a maximum training time. I just did a one-click, so it's going to do 30 minutes. It's going to run longer than we're going to wait. So I did one last night. We're going to play with that one, just so you know. But you can tell it what to optimize on. So by default, it's going to try to optimize across all 4 supervised learning techniques for classification in this case. But if I didn't want it to use deep nets or something, I could take those out. You can tell it how it's evaluating each one of these models as it progresses. You can also tell it what metric to optimize by. So if you knew, for example, that you were doing some kind of maybe a fraud detection and you wanted to optimize your recall, you could optimize this by recall and pick a specific class. Okay, and now it's going to choose models that are only performing in that one metric. All right, so you can optimize this very specifically for the metric you want. By default, it does the phi coefficient, which is why we're using it. And let me show you what it looks like while it's running, because it is kind of pretty, what it does. Okay, so there we go. It's cruising along. It hasn't actually started doing any evaluations yet, but you see it made some training and test splits. It's done 4 logistic regressions and 3 neural networks, 7 different ensembles and 3 trees. And once those are all built, it's going to evaluate them and use those results to guide which of these to try next and what parameters to use for each one. And it's just going to keep going until it comes up with what it thinks is the list of the best possible functions. Okay, so let's take a quick look at our evaluations so far. All right. 1 hour and 6 minutes, 2 minutes. Oh, yeah. You know, just to make sure I don't get myself confused, let's delete those 2. I really enjoy deleting things. Character flaw of some kind, I'm sure. Okay. Oh, I didn't do the deep net. Oh, that's what I forgot. Apologies. So we have the neural network too. Let's get him going. Evaluate. Test. Okay. Okay. Take our evaluation and let's compare them all. Compare multiple evaluations. Please do. Okay. Fantastic. All right, so far, we have our single tree down here at the bottom with a 0.75. Is that right? Yeah. Okay, and the, well, these are the AUC, what I need. We can't compare them this way. I'm sorry, I forgot. We have to look at them individually because I need to show you the phi coefficient. Okay. So exasperating. Okay, single tree has a phi coefficient of 0.36. All right, not too bad. A little low. Okay, let's see how the one-click ensemble did. So the one-click ensemble got a 0.62. That's a lot higher than the single tree. That's nice result. Okay, let's how about the one-click logistic regression? 0.508. Okay, so somewhere in between those two. Let's see the one-click deep net. All right, a 0.67. Okay, let's see how much those change from what I had last night. Okay, but now let's take the OptiML. So let me show you what it looks like when it's done. Okay, so what you get out of the output is you see all the evaluations it performed there. And down below, these are the optimized models that it found. Okay, and so in particular, we see at the very top for what it found was this logistic regression with some very specific parameters. And of course, these all have different parameters. That's the game we're playing here. So these are all different possible logistic regressions that it discovered that seem to do very well with a very specific set of parameters. Okay? And this is going to change when you change your data. That's the game we're playing here. It's for your data, for these parameters, that logistic regression does very well. And it did better than pretty much everything else that it discovered in this run. Okay, this is a bit of a random process, so sometimes you can get slightly different results. Okay, if we would like to see that top model to really know how well it performed, we need to do an evaluation, right? I can't just trust this ROC that you're seeing here because this is on its testing that it did, but basically a cross-validation. To know how it's really comparing to everybody else, to be fair, we need to use the same test set. All right? So we can take this logistic regression, okay, from the OptiML, from those optimized resources, and we can go ahead and evaluate this one as well. Let's not evaluate it on the training set. That would be awkward. Okay. All right. Now, the thing I want you to notice is how much higher that phi coefficient is. Okay, the last logistic regression, remember, was a 0.5 or something, or 0.4? I forget exactly, all right? Which is why I have a slide. So let's do the slide real quick. And these may not be exactly the same, unfortunately, but it should be fairly representative. So we had the one-click decision tree, 0.36, that sounds right. We had the one-click logistic regression, was about a 0.4, okay? And notice that the OptiML process generated a logistic regression that did a 0.6. So it actually found a way to parameterize a logistic regression that improved it significantly, okay? That's interesting. The one-click ensemble is also nice because it did much better than these two algorithms, but not as well as an optimized logistic regression. Okay, a relatively simple algorithm, but with the parameters just right, you get this performance out. And we also see the one-click DeepNet, which is basically on par. Those are pretty close, but that's also nice to see that those are playing well together. So what we'd like to know is what else can we try? Okay, how else can we squeak a little more performance out of this? Okay, so the key insight here is that machine learning algorithms each have unique strengths and weaknesses. And what we're going to do is fuse them. So we want to just take any kind of models and glue them together into a new model. It's a bit like stacking, but don't think about stacking in this regard. Okay, this is a little different. So the caveat here is they have to have the same objective type. Okay, you can't fuse a regression and a classification. Okay, they both need to be classifications. But the inputs in the feature space can differ. So you can train a model on a subset of features and train another model on another subset of features, and you can fuse those together, and that works just fine. Okay, your new model just has all the features as inputs. That's no problem. You can add weights, so you can say, I want to fuse these models, but this one is twice as important as that one. Okay? You can give more importance to individual models. Fusions can be fused as well. You can do a bunch of fusions and fuse those fusions together, and you can get as meta as you like. All right? It's especially useful for fusing these OptiML models. Okay, so you can take the output of OptiML, it's generated a bunch of models it thinks are really good performers, and you can fuse them together and maybe make something better. Okay? Why would that do anything? Right? The idea is that we're going to take perhaps the best DeepNet that OptiML find, and the best ensemble, the best logistic regression, and make a new model that fuses them all together. And maybe that'll be even better. It's possible. Let's try it. So in this case, I'll do a very specific, we could just take the top, but I like to do this with kind of this diversity idea, so let's do that. So we'll take this top logistic regression, okay, and a top looks like a random decision forest there. So we have a random decision forest. Here is we'll just take the top forest, that's fine. Okay, so we got the top forest. It is always funny how this is a little bit different. So we have a logistic regression, we already have a forest. Here's the top neural network that it found. And what am I missing? A single tree, right? Let's get a single tree too. There's probably one in here somewhere. Maybe there isn't. It's usually one single tree hiding somewhere. Oh, there's one. Okay. Now, to be completely honest, I don't know what this will do, because this is a random process, and these are a little different every time you do this. But did I get everything? Let's see. One logistic regression, one ensemble, one neural network, and one tree. Okay? And we could add more if we wanted to, but let's go ahead and fuse those together. Why not? And let's first observe that this works just like any other model in BigML. We get a partial dependence plot. We can explore the decision boundary of this new weird fused model thing. We can use it to make predictions. Everything works the same way as a regular BigML model. In particular, we can evaluate it. So let's do that. On the holdout, evaluate. You can do it. Okay. 0.67. Okay. That is a little bit better. Okay, I got 0.68 last night. All right, does that 0.674? Okay, so last night it was like a 0.675 something. So, okay, so I did get it. So, okay. But this is the game you can play with fusing the output of OptiML. We're definitely competing with that one-click DeepNet. We could also try just taking the top OptiML models. That would probably work better, but I wanted to do something a little more fun with a little diversity. But now we're going to do something even more different, perhaps. What else could we do? First, let's think about fusions a little bit. When we're fusing, it's basically just, if you have 3 models here, it's making the prediction for each one, and then it's just gluing those predictions together. It's literally what it's doing. Okay, so you can see how this isn't stacking. There isn't a model on top of the model. It just takes the models independently, looks at the probabilities and the weight you assigned, and computes a little function to tell you what it is. All right, it was true, and that one's false, so the output's true. And same for a regression, it's basically just doing an average. Okay? It's fully accessible through the API and WisML, the bindings have support, everything works the same, it's just like any other model. But there's some cool stuff you can do with fusions other than just look for performance, so it's worth mentioning them. One is that Charlie was mentioning the other day, if you really like the interpretability of decision trees, sometimes you don't like the abruptness, right? This whole region here, nothing changes. This patient has more and more plasma glucose, and they have the exact same diagnosis, and then all of a sudden there's like one value where if you just have 0.1 more plasma glucose, suddenly you have diabetes, right? And that's a little bit unsettling. It's like if you could just lower your glucose by 0.1, you'd be fine, okay? Maybe for the domain you're in, that could be unsettling, but you don't want to lose the interpretability of a tree, and so you could potentially fuse it with another model that has a smoother boundary and get something that's a bit more responsive, at least in that region where the boundary is. Because you still have sort of the dominance of the tree, but you can add something that has a smoother boundary and kind of smooth out those regions where things aren't changing. Okay, that's one thing you could do with a fusion. Another is this idea of feature stability. Okay, you might have, let's say, 100 features in your data set, and it might be that there's a subset of features, let's say 2 subset of features, that are equally good at making predictions. Okay? You could model these 10 or those 10, and you get models that work exactly the same. All right? But at prediction time, you may not know all of the features. And so when you build your model, it's just going to pick some, and maybe it picks these 10, and at prediction time, you only know these 10, and so your model doesn't know anything. And that can be a little unsettling, right? You're trying to put values in, and the model goes. And so what you could do is you could build models for those 2 different subsets of features, and now it doesn't matter what you have on the input. One of those models in the fusion is going to know an answer, and the output will be stable. Okay, so you can fuse these different subsets of features that have similar modeling performance and get that resilience. You can also do weighting over time. There's the idea that your data has significance over time. So your data may change significance. You have short-term user behavior versus long-term, for example. Okay? And what we can do is we can set weights to account for the significance. So I can build a model that's just 1 day of data, and I can build another model that's 1 week, and a model that's 1 month, and then I can build a fusion that says, consider everything from 1 day with a weight of 8. So the model is regarding data from the last day very importantly, but it's not ignoring data from a week ago or a month ago, it's just with less importance. So I'm adding historic context, but with a tapering importance. Okay, so the freshest data is the most relevant, but I don't lose, I'm not just cutting it off and filtering 1 day of data. I still have a whole month, but with a tapered importance. All right, so I can make a sort of a custom model that way. Maybe you want to improve your class separation. So maybe you have a 3-class objective. That's something we haven't really played with, but you got yes, no, and maybe. Okay? And this happens more often than you might think. But you really only care about yes versus not yes. You don't really care if it's no or maybe. You just want to know if it's this or one of those 2. All right? But the problem is that a single model might struggle to separate these 2. Remember, it's trying to make a classifier that does all 3. And so it's going to spend a lot of time trying to split the no from the maybe, and you don't actually care. You don't want it to do that. And so what you can do is take your original data set that has all yes, no, and maybe, and you can make one data set that's just yes, no. Just remove the other class, take it out. So this model only has to distinguish yes from no, and then you take out the no's, and this model only has to distinguish yes from maybe, and then you just fuse those back together. And so you've allowed this model to focus on yes versus no, and this one to focus on yes versus maybe, but the final result can distinguish all 3 equally. Okay, nice little trick. Now I'll give you one more. Some machine learning algorithms just generally do better on some feature types. Okay? So a random decision forest, when you're using these sparse text vectors, generally just does better. All right? It's very good at these sparse data sets, and text vectors are sparse, so it tends to do a little better. Logistic regression and deep nets tend to do better for numeric features because their numeric features tend to engender these very smooth decision boundaries, and they're fine-tuned for those. Okay? Trees, single trees, tend to excel at categorical features, right? Because you have discrete values, and the tree is all about splitting. Because you don't have to worry about these weird diagonal boundaries. It's yes, no, black, white, red, green, and it just goes split, 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 split. Everything's perfect. So why don't you just take your data set here and split out all the numeric fields and build a deep net there, and take out all your text fields and build an ensemble there, and then fuse them back together. And let this model focus on only numeric, and let this one focus only on text, but have a model in the end that does both. Yeah? Let's try that. Let's see how that performs, and let's hope for the best here. Okay. All right, so all I'm gonna do is take my training set, and I'm not gonna be super fancy. Okay, I'm gonna configure an ensemble. I'm not gonna do any configuration on the ensemble, no parameter optimization, just the default. All right? But for this ensemble, I'm going to take out all of the features except for the text field. Yep, training set. So this ensemble is only learning from the boilerplate. It's only thinking about text. Okay? And while that's building, let's go back to the data set. And let's also build a neural network. So we'll configure a deep net. Again, I won't do any optimization. We're choosing the label, that's perfect. But this time I will remove the boilerplate. So this deep net will only learn from the categorical and the numeric values. So it will not learn from the text at all. But no optimization beyond those two steps. Wow, excuse me. That was a powerful cough to wake up everybody. Power cough. Okay, come on. It's late in the afternoon, I'm getting silly. Oh, you can do it, DeepNet, come on. Oh, I forgot to turn off the Wi-Fi. In progress, 85%, 96%. Yes. Okay. Okay. And let's do our fusion. So this time I'm just going to start from this deep net and we'll create our fusion. And then we'll add our ensemble. Yes, I want that one. Pretty sure that's right. Okay, we'll create the fusion. So again, we're just fusing two. One ensemble that was trained on the text, hopefully I did that right, and one that's a neural network trained on everything but the text. And let's evaluate this. Okay, 0.6. Not as good as last night, darn it. Man, I got a 0.7 last night, come on. All right, okay, well, you get the idea. But it is still relevant, even though it wasn't the top performer like it was when I experimented with this last night. Realize that what we just did with this very simple fusion I created is we got a 0.6, which is up here in this upper echelons of performance, but with no optimization. Okay, I didn't optimize the ensemble, it's just 10 trees, very simply built. I didn't optimize the neural network. I didn't do any long calculation that was much quicker than the OptiML is still running, okay? And the OptiML it's in the same category as this OptiML, right, at 0.6. So there are ways to get performance out of your models that aren't just running optimization algorithms, and not also just guessing across lots of different algorithms, okay? There's things you can do in the feature space, and the reason why I like this story is because the features are often more important than the actual algorithms themselves. And this is a really good example of basically playing with the features. Yeah. Okay, sorry, I ran over, but we're done. That's it. Whew.
Any questions before we go to lunch? Yes.
Yeah, I'm hungry.
Hi, I'm not sure if it was just a matter of time for the presentation, but I'm not sure if, so when you apply feature selection, feature engineering, whatsoever, you're using the same data set as it will be further used for building the model? And if yes, is it a good practice versus having a separate partition only for feature engineering and then use another one for training the model?
I didn't understand your question. Is it about the feature selection?
Yeah, so I mean, is it a good practice to have a separate data set just for feature selection and don't use the same data for training the model? Or is it okay to use same partition for both operations?
I'm not sure. Maybe I still don't understand because I don't see the problem. I mean, you wouldn't normally need to have an isolated data set for doing feature selection. You certainly can, right? Because you can just filter the data set and create a new data set that removes them for sure. Or you can just do like I did and take some out when you're modeling. Those are functionally equivalent. You're not going to get a different result in that regard. And at least in BigML, when you do that, the model is going to know what features you used, so you don't lose that information. Right? It's certainly more rigorous if you filter the data set and extract the features and say this is the one I'm going to use. But it's the same, and you're not going to lose the information.
Okay, so well, rather than losing information, I was more worried about potential overfit by using the same data set for training the model and before for doing the feature selection. Is that all right from that viewpoint? Or?
Yeah. So it just depends on how you're doing the feature selection. No, okay, now I understand what you're talking about. So for example, if you're doing one of these algorithmic procedures, the one that I'm thinking of in my mind right now is like
L1 or L2, you mean? Or?
Like best first, you know it? So in a best first, what you do is you say, I've got 100 features, and I want to know what the 10 best are. And the quality for best is, it takes one feature, actually. If you have 100, it builds 100 models, each model with just one feature. And it looks at which model does the best with just one feature, okay? And whichever one does the best, it keeps that one feature. And then it repeats the same thing 99 times, pairwise. This one with that one. This one I liked with that one. This one, it does that. And it keeps doing it until it builds up a little family of the top, whatever you wanted. If you said 10, it's going to go until it has 10 best first. And in that regard, that there's no leakage to be worried about, because you're actually asking it, when I model, what are my 10 best features here? And that's exactly what you're evaluating in that algorithm.